Hello guys, welcome to our YouTube channel. Today we are going to discuss about the S parameters, also known as scattering parameters. This is the table of content where we are going to see what are scattering parameters, what are the different types of it, like insertion loss, return loss, and how does the touchstone file looks like. S parameter or scattering parameters, nowadays they have become a very important and vital part in order to analyze a transmission line basically. So the interconnects can be modeled in the form of frequency domain with the use of S parameter or scattering parameter. So what does scattering parameter does? Scattering parameter shows the degree to which the sine waves are reflected or scattered from the signal source of the known impedance by each pin, terminal or the ports that are being created, and the amount of signal that is being deteriorated from its original path. For example, if we take a sine wave here, as you can see in the example, it's a sine wave. So if at the receiver end, if my sine wave is being distorted a little bit, as you can see, I am just adding some distortion over here. So if the sine wave is being distorted, then at the receiver end, I'm seeing a distorted sine wave. So the reason behind this distorted sine wave may be multiple reasons, like the impedance mismatch, as I have mentioned here, the coupling between the ports, or we also call it as a crosstalk. So what does we get as an output of the scattering parameters? So the output of scattering parameters, basically we got insertion loss, and we get second is the return loss, and we also see the crosstalk values. Okay, so these are the basic results that we used to get while analyzing the scattering parameters in a transmission line, or we can say in any interconnect. So first of all, we are going to discuss about the insertion loss. So what is insertion loss? So the basic definition for insertion loss is the ratio of transmitted voltage to the incident voltage into the interconnect. So let me explain you this thing in a very easy way. So if it is my transmitter, and if I'm having a transmission line in between, and this is my receiver. So the signal transfers from the transmitter, it goes from transmitter and it got received at the receiver. So some part of the signal, so for example, if 100% of the signal is being transmitted and if 95% of the signal is being received at the receiver, so that 5% which is being lost in during this transmission part, or what we call the transmission line or any interconnect, so the amount of signal got lost in this interconnect is known as the insertion loss basically. Okay, so as the definition itself says, the ratio of transmitted voltage to the incident voltage into the interconnect, means transmitted is this one and the incident is this one. Okay, it provides information about the interconnect losses. Okay, so what does this mean? This means the whatever this 5%, whatever we were discussing about, this 5% loss is the loss because of this interconnect, or what we call the transmission line that we have taken here. So the losses inside this transmission line. So basically when we talk about the insertion loss, it talks about the transmission line losses or the interconnect losses. Okay, so how does we see the transmission line loss, or how does we see this insertion loss? So the insertion loss plot looks like this. So it's basically the loss versus frequency graph. Okay, so whenever you are taking a linear graph, so the value of transmission line, the value of losses deals between -1 and 1, and whenever you talk about the logarithmic, so whenever you put these losses under logarithmic, then the value is 0 to negative. Negative can be any value. Okay. So in case of a perfect lossless or perfectly matched ports or interconnects, we will get the insertion loss as 1. So when we talk about 1, it is for the linear, that is the maximum that we are getting. And when we talk about logarithmic, that should be 0 dB. So how does a plot looks like for an insertion loss? I'm going to show you that plot also. So as soon the frequency increases, so the attenuation also increases in the transmission line, right? It's because of the losses of the copper as well as the dielectric. So the copper losses and the dielectric losses plays a major role here. So if you have a copper loss or a dielectric loss at a higher value, then there might be a chances, or there are speculations like if your insertion loss is very high, then these might be the reasons behind them. So we call them as the materialistic losses. Materialistic losses. Materialistic losses. Okay. So attenuation increases as frequency increases, as it shows. The value of insertion loss increases in dB negatively. Okay, so as you can see for this one, for example, if the value is 0 and this one is minus 10 dB and this one is minus 20 dB, and this shows the frequency. And for example, here it is 1 kilohertz and here it is 100 megahertz and here it is 1 gigahertz. So at 1 gigahertz, if you see, so you're getting a loss of around minus 20 dB. So this is what the insertion loss at 1 gigahertz. Okay. Now let me explain you how you're going to see this insertion loss, like how to minimize this insertion loss, or how you are going to judge as if the insertion loss is better or not. So the value of insertion loss should be nearest to 0 dB, or if we talk about the linear, then it should be nearest to 1. So the value of insertion loss should be nearest to 0 dB. So for example, if we take a scenario where the insertion loss for a transmission line is, for example, TL1, for TL1 that the insertion loss is minus 20 dB at 1 gigahertz. And if we talk about the TL2, where the insertion loss is, for example, minus 12 dB at 1 gigahertz. So in this case, transmission line 2 is a better transmission line, or we call it as the transmission line is being, the materialistic losses are less in the transmission line. So the insertion loss mainly get, like the signal mainly get attenuated in the case of insertion loss is because of the materialistic loss that we are going to see. This is how the insertion loss plot looks like. As I already explained, so the value is in dBs here. And as you can see, the values are getting negative. That means the y-axis is explained in the form of logarithmic. That's x-axis. X-axis is in linear and the y-axis is in logarithmic. As you can see, the value starts from 0 dB and it is keep on deteriorating with respect to the frequency. So as you can see, at 14 gigahertz, the frequency has been minus 11 dB. So at 14 gigahertz, the insertion loss is at minus 12 dB. So at lower frequencies, as per this example, at lower frequencies, so if I take around 8 gigahertz for a lower frequency, let us take 4 gigahertz. So at 4 gigahertz, it was around 1.5 dB, minus 1.5 dB. And at high frequency, as you can see here, at 14 gigahertz, it's around minus 11 dB. So the value of insertion loss should be nearest to 0 in order to be a better transmission line or the better transmission of signal. As I already explained, the amount of signal getting lost between TX and RX, the amount of signal getting lost between TX and RX is basically the insertion loss. For example, if I am explaining it again, 100% of the signal get transmitted and it got incidented only 95% of it, then the 5% of the signal got lost in the form of insertion loss. If you have any doubt, you can comment down below. I'll explain you in other better ways. So let us discuss more into the return loss part of it. So what is return loss? So return loss is basically the ratio of the reflected voltage to the incident voltage in the interconnect. So let me explain this part. So for example, if you are having a transmitter here and an interconnect here and a receiver. So as you can see, the signal transfers from transmitter to receiver. For example, if 100% of the signal is getting transmitted and for example 95% of the signal I'm seeing at the receiver, that means 5% of the signal get lost somewhere. So as I already explained, it is because of the insertion loss. But what is return loss? Return loss, as the name itself says, as the name itself depicts, return means the amount of signal that gets reflects back at the transmitter due to the interconnect or because of the receiver. Okay, let me reframe it in other ways. So for example, if 100% of the signal got incidented and some part of the signal get reflected, for example, 5% of the signal get reflected back and 95% of the signal is been received here. So this 5% which got reflected back to the transmitter itself, this is known as the return loss. Okay, so as in the insertion loss we have already discussed, so insertion loss is because of those materialistic losses. Then how this return loss happens? So the return loss basically provides you information about the impedance mismatch of the interconnect. So whenever there is an impedance mismatch in the transmission line, or what we call impedance mismatch between the transmitter and the transmission line, then impedance mismatch happens. So if you need to know more about these kind of impedance mismatch losses, how these are cured, these are cured by the termination techniques. We have already made a video on termination techniques. So if you want, we'll put up in that column, in that I button here. You can click on the I button here and you can see those videos. So in that video, we have explained about this impedance loss, crosstalk, and we have talked about how to cure the impedance mismatch losses. So let me give you a brief, like how it basically happens, why this loss happens. Actually, for example, if your transmitter, if the pin of the transmitter is at 40 ohms or what we call 50 ohms of impedance, and if your transmission line is matched up at 40 ohms, so there is an impedance mismatch between them. So in order to reduce this impedance mismatch, so because of this impedance mismatch, some part of the signal get reflects back to the transmitter in the form of return loss. So as the frequency increases, this loss will become more and more. So there is an impedance mismatch between them. So how you are going to cure it? You are going to add a series termination resistor of 10 ohms so that the cumulative impedance becomes 50 and 50-50 get matched, and the match with with this matched impedance, maximum or 100% of the signal gets transmitted. So this only happens in the case of ideal case where 100% of the signal get transmitted, even though some part of the signal gets reflected back. So as this principle of return loss moves exactly the opposite what we have learned in the case of insertion loss. How? So the larger the value in negative dB, the better is the impedance matching. So let me take you through the graph of a return loss. So if you talk about linear, as again I am explaining, in case of linear the value of losses are between -1 and 1, and in case of logarithmic it is 0 to negative values. Okay, so in the next slide I'm going to explain you in a better way about how this return loss plot looks like. So in order to reduce the return loss, you are having the termination techniques and you will work on the crosstalk, reducing the crosstalk. In order to reduce the crosstalk, there should be a good coupling. So we are planning on preparing a video on crosstalk, and even though we'll provide that in that I over here, so you can go through that crosstalk video, and it will be more better for you to understand about it. What is crosstalk? So we have already created one video on termination techniques, and we are planning on creating a video on crosstalk now also. Let us see the written loss plot here. So as I told you, like this is already a linear plot, not a linear plot, sorry, logarithmic plot. So logarithmic plot starts from 0 dB, as you can see here. Somewhere here is a 0 dB, and it is going till minus 52 dB. So the return loss is minus 52 dB at low frequencies. See, as if you can see here at 0 gigahertz, the frequency was the value of return loss is minus 52 dB. So what we are going to see here is if your impedance mismatch is high. I'm talking about the impedance mismatch, not impedance matching. If the impedance mismatch is high, then the value of return loss will be low. How it is, I'll just explain with the help of this diagram actually. So as you can see here, we have 7 gigahertz frequency. So at 7 gigahertz, we are seeing this dip here. As you can see here, the graph is going above part, and at 7 gigahertz, if you notice in the graph, we are seeing minus 6 dB of return loss. What does this mean? This means only 6 dB or only very less part of the signal is going through like going to the receiver, and maximum of the part is getting deflected back to the transmitter. That is the reason, as I told you earlier also, nearest the value to 0 dB, more is the transmission at that receiver end. See, so if the receiver end is getting, that means this value, at this value, the return loss is very high, very high. See, the return loss is very high. So what did we get from this example? The observation that we made from this example is the return loss values. So return loss value should be more negative. If you have more doubts about it, please drop down some comments. We are going to reply to them. And if you are still not clear, then we'll try to make a few small videos just to explain the concept about it again. Now let us see how an S parameter file looks like. So S parameter file. So what happens when you have done your S parameter extraction, you are able to see the insertion loss plot, and you are able to see the return loss plot also. So how you're going to use these return loss and insertion loss plot in a channel simulation. So the output of this simulation itself are in the form of two files. Two files are created by this. One is .bnp, or also known as .snp, and one is .ckt, that is the circuit file actually. Okay, so let us talk about the touchstone file. So the .snp or .bnp, these are the touchstone file format that we are having. So as you can see here, those versions of Spice capable of running S parameter models nearly universally use the touchstone file format. So the touchstone file format is a standard format that has been used in order to depict the S parameter data. Okay, so what does a touchstone file has? Like, what is the content of touchstone file? Case of a touchstone file, all the details about each and every part of the frequency versus impedance graph is being shown over here. Okay, let me explain you in a better way. So it will have magnitude of the loss, as well as the phase of the loss. Magnitude and phase, or we can call it as degree of the loss. Okay, so for insertion loss, return loss, at each frequency, what is the magnitude of the impedance and what is the phase of the impedance? Similarly, for return loss, what is the magnitude of impedance and phase of the impedance? So this touchstone file has all the informations about the S parameter extracted through it. And usually S parameters are being specified at 50 ohms. But any reference impedance may be used. You can use any reference impedance instead of 50 ohms. Usually 50 ohm is being used in the industry as an industry standard. If you want, we can make more, we'll make more video of why we only take 50 ohms instead of taking some other videos. So in case of single-ended, we usually take 50 ohms, and in case of differential, we take nearly 100 ohms or 90 ohms, like that. So it depends on the specifications of the interconnect also. So as I already explained, the touchstone file format BNP and SNP are the touchstone file formats. So that's all for this video. So in this video, we have seen multiple things like what are S parameters, and what are the types of S parameters, basically insertion and return loss. We gone into the graphical representation of insertion loss and return loss, and we have seen the format of a touchstone file, how a touchstone file looks like, and what are all the informations which are available in the touchstone file. If you have any doubt or any clarifications, please drop down the comments below, and we'll try to answer all your questions. And please hit a like and subscribe to our channels. This will motivate us to create more useful videos for you. And if you want to see a new series on power design, just do let us know in the comments. We are coming up with the new sessions for power design as well. Thank you. Have a good day.